solid over solid here. So the other includes Naoto Shiraishi, and he will give us a magical talk about alchemy of quantum coherence. So itself.
Thank you for introducing. I'm Naoto Shiraishi from the University of Tokyo. Today I'll talk about the resource theory of U1 asymmetry. And in particular, we show that the unspeakable coherence can be amplified arbitrarily. My talk is based on this paper. So if you can please see this paper. Before going to my talk, I like to remark that this talk have many overlaps between previous talks by Ray Ganelli. In fact, our paper and Ganelli co-authored paper appeared on arXiv on the same day. And in fact, we treat a very similar subject and we obtain a very similar result. So these have many overlaps. Okay. Now, this is the outline of my talk. First, I'll explain the background of my research. As I mentioned, we treat the unspeakable coherence or U1 asymmetry. If I say simply coherence, then I mean that the unspeakable coherence. I'm sorry for colleagues who study the speakable coherence. And in this theory, the free operation is a covariant operation. In this talk, we particularly treat two frameworks. One is the marginal asymptotic conversion, and the other is a correlative catalytic conversion. Because Ray have already explained correlative catalytic conversion in detail, so I'll skip this. But maybe marginal asymptotic conversion is slightly a new notion, so I'll explain it. Usually, in the conventional asymptotic conversion, we measure error over all copies and all desired copies. But in the case of marginal asymptotic conversion, we consider a reduced state of the obtained state and compare it to the desired state. And we quantify the error by its maximum. By definition, the marginal asymptotic conversion is a stronger conversion power than the conventional asymptotic conversion. But maybe it is presented tomorrow. In many resource theories, marginal asymptotic conversion and asymptotic conversion have the same power. So in this talk, we treat marginal asymptotic conversion as the asymptotic conversion without explicitly mentioned. We now provide one previous result which provide a negative implication on the coherence manipulation. No broadcasting theorem. No broadcasting theorem treats correlated catalytic conversion, and this theorem states that if the initial state is incoherent, then the final state is also incoherent. So this theorem states that in this setup, the correlated catalyst provides no advantage on the state convertibility. It is a very negative implication on the coherence manipulation. On the other hand, we have a completely opposite implication. This result is shown by Ryuji and I in this paper that we have multiple catalysts and the catalysts can correlate with each other, then we can perform arbitrary state conversion. So we can convert, for example, incoherent state into maximally coherent state. So these two are very opposite implications, and the situation is highly controversial. We want to clarify a first aspect is more close to the real. Now we move to our main result. To state this, we shall define a coherence on relevant modes in the initial state. This we use the symbol G, which is used in the I word J in the Ray's talk. Here we define delta Ij as the energy level spacing between the energy eigenset I and J. Then we say that inclusion relation with C holds if any coherent mode in the low prime final state can also be written as a linear combination of the coherent mode in the initial state rho with integer coefficients. But we also have another characterization. The inclusion relation with C prime, which holds if any coherent mode in the rho prime can also be written as a linear combination of the coherent mode in the initial state rho with rational coefficients. So we have two definitions of the coherence of relevant mode. But remark that in both cases, the amount of coherence is irrelevant. So maybe the initial state has extremely tiny coherence, and the final state, rho prime, has a very almost maximal coherence, but the inclusion relation with C or C prime may hold. Now we state our main result. Our first result is on the marginal asymptotic conversion. We assume that the inclusion relation with C holds. Then the transformation rate from rho to rho prime diverges. In addition, if the final state is full-rank, then this conversion is exact. In addition, the correlation between a single copy and others can be suppressed arbitrarily. So this theorem implies very striking phenomenon that very few low coherent states can be converted into arbitrarily many high coherent states. It's very extremely counterintuitive. But our theorem states that this protocol indeed exists in the covariant operation. On the other hand, we have a completely opposite theorem. We assume if the inclusion relation with C does not hold, then the transformation rate is 0. So there is two extreme phase, and there exists a very sharp threshold. One side is that transformation rate is infinity. The other side is that transformation rate is 0. And this sharp threshold is given by the inclusion relation with C. We next state our main result on correlated catalytic conversion. Assuming the inclusion relation with C holds, then rho is convertible to rho prime with correlated catalyst. In addition, the correlation between the system and the catalyst can be arbitrarily small. And similarly to the previous case, if the final state is full-rank, then this conversion is exact. On the other hand, we have a corresponding no-go theorem, which we call no mode broadcasting theorem. This is an extension of the previously explained no broadcasting theorem. Assuming the inclusion relation with C prime does not hold, then rho is not incompatible to rho prime, even with the help of correlated catalyst. We expect that this is just a limitation of a technique. This condition can be replaced by the inclusion relation with C, but it is remain as a conflict future work. Okay. Now we construct two protocols and prove the no-go theorems. We first construct a protocol of marginal asymptotic conversion by using the marginal catalytic conversion with so the multiple catalysts. As we explained, if we have multiple catalysts, we can achieve arbitrary conversion. We in particular consider the case that there are two marginal catalysts. And we prepare two sets of two marginal catalysts. Of course, we have two conversions, but then these two catalysts correlate with each other, and we can no longer use these catalysts again for the same task. But by rearranging the catalyst, because this catalyst and this catalyst does not correlate, we can perform additional two conversions. So we have totally four conversions from two sets of marginal catalysts. And if we have four sets of marginal catalysts, we have additional four conversions as this. In general, if a marginal catalyst consists of n catalysts, then k power n set of marginal catalysts admit not k power n conversion, but k times k power n conversion. And this, so we can partially reuse a catalyst, and this is very important. Our second idea is coherence distillation. We can distill one set of marginal catalysts from maybe many but finite copies of initial state rho. We denote by mu the number of copies for this distillation. We here remark that usually the coherent distillation protocol is provided only in the approximate form, but fortunately we have a tool to construct the exact distillation protocol from this approximate distillation protocol. This lemma shown by wielding the chair proved this fact. Roughly speaking, let S is a set of state which is achievable from a given set rho with arbitrarily small error, and assume that the desired state rho prime is an interior point of this set S. Then rho is convertible to rho prime exactly. This is a statement of the lemma, and using this idea, we can obtain an exact distillation protocol from the well-known approximate distillation protocol. Now we construct a protocol. We first prepare mu times k power n copies of the initial state rho, and we using the distillation protocol, we construct the k times k power n sets of marginal catalysts. Then we prepare the initial state. We prepare k times k power n incoherent state, which is a free state because they are incoherent. And using this marginal catalyst, we obtain k times k power n copies of desired state rho prime. Now we compute the rate. The rate is k over mu. Since mu is a fixed number, but we can set k arbitrarily large, so we have arbitrarily large transformation rate. Okay, this is a construction. We finally comment on how to suppress the correlation between copy and others. To suppress a copy, we first transform the state not into the desired rho prime, but close a state close to the pure state phi, and this state can be distillable, can be distilled into the desired rho prime. Because a pure state have no correlation, these a state close to pure state have arbitrarily small correlation. And then we distill these states into the desired state rho prime. Because a separate operation cannot increase the correlation, these final states have arbitrarily small correlation. Okay. Now we next construct the protocol of correlated catalytic conversion by using marginal asymptotic conversion. We suppose that there exists a marginal asymptotic conversion from 6 copies of rho to 6 copies of rho prime. In this case, we construct the catalyst as this. Here, vertical axis means the different system. So the catalyst consists of 5 copies of the system and 1 register system. The horizontal axis means different states, and we mix them with equal footing. So in this case, we prepare 6 different states with equal weight 1 over 6. Here, this orange state is a reduced state of the final state of the marginal asymptotic conversion. Now, the initial state of the composite system can be written as this. Now, we apply the marginal asymptotic conversion as this. Then, by regarding these systems as a catalyst, then the state is exactly the same as the initial state of the catalyst. So this is indeed the catalyst. In addition, because of the definition of the marginal asymptotic conversion, this state is close to the desired state low prime. So we obtain correlated catalytic conversion from marginal catalytic conversion. Now we move to the proof of the no-go theorem, particularly no-mode broadcasting theorem. Our first basic no fact is that mode of asymmetry. If initial state has no coherence on a mode, then the covariant operation cannot create coherence on this mode. This lemma directly implies the no-go theorem on marginal asymptotic conversion. Okay, it's simple. But unfortunately, this technique does not apply to the correlated catalytic conversion. Because even if the system has no coherence, maybe the catalyst have a coherence on the same mode. So the composite system, the initial state of the composite system have a coherence on this mode. So the mode of asymmetry, the argument of the mode of asymmetry does not apply. But fortunately, this conversion, creating no coherence from no coherence to final coherence with a correlated catalyst is prohibited by no broadcasting theorem. Okay. But the scope of no broadcasting theorem is slightly limited. Because let us consider this case. We consider a system which has two energy mode 1 and square root 2. And mode 1 has no coherence, but mode square root 2 has coherence. And we want to ask whether we can create a coherence on mode 1 in the final state with the help of correlated catalyst. The answer appears no, because the coherence on the mode square root 2 appears to play no help to create the coherence on mode 1. But because this initial state is coherent state, no broadcasting theorem does not apply. So we want to extend this result. And no mode broadcasting theorem indeed do this. Because the condition, the inclusion relation with C prime can be written in this setup. So the inclusion relation with C prime does not hold in this case. So the no mode broadcasting theorem indeed prohibits this type of conversion. Now we shall prove this theorem. To prove this, we employ science frame duration picture. So we apply energy constant unitary on the system, catalyst, and a local system whose initial state is incoherent. Then we can embed all the dynamics into radar systems. So the radar system is a fixed energy level spacing system, and in this case, for example, the radar with spacing 1 square root 2 and blah blah blah. And the benefit of this picture is that all dynamics occur inside each radar system separately, because we apply only the energy conserving unitary. So the dynamics we can analyze inside each radar separately. Now our key observation is that if we can convert this state into this state through a covariant operation, then this conversion is also must be possible through the covariant operation. Here, the density matrix of this and this are the same, but the energy level spacings are different. This conversion must be possible because in the covariant energy constant unitary, the value of the energy level spacing is completely irrelevant. Now we prove our desired no mode broadcasting theorem by contradiction. We suppose, contrary to our claim, that this conversion is possible through covariant operation. So the system does not have a coherence on the radar 1, but it has coherence on the radar 1 in the final state. And the catalyst should return to its original state. If this conversion exists through the covariant operation, then this conversion must exist because of the previous argument. Here we said all the ladders, energy spacing in the ladder to 0, except for ladder 1. Then all the ladder except ladder 1 the states in these ladders become incoherent because all the states are degenerated. Now, we find that the initial state of the system is now completely incoherent. But the system has a finite coherence in the final state. So this conversion is prohibited by no broadcasting theorem. This is contradiction. So we now prove that this is no mode broadcasting theorem. Our idea is that if the counterexample to no mode broadcasting theorem exists, then using this we can construct the counterexample to no broadcasting theorem. Okay. This is a summary of my talk. Thank you for listening.
Thank you very much for the very interesting talk. So we've now seen that for coherence, you get this very nice amplification. Can you comment on non-commutative groups? So asymmetry from non-commutative groups, do you have any hopes?
I think it, because my interest is in very similar to the layers, so my interest is on the energy conserving thermal operations, so I just treat only U1 symmetric case. But I expect that there are other groups, asymmetry on the other groups I expect, but I'm sorry, I think you usually try to some of them, and I heard he had some progress, but so I think it is possible, but I'm sorry, I didn't try it. It's kind of hopeful.
More questions? Okay, then let's go on, and thank you again for the nice talk.